Morning, everyone, and welcome back. What did we end up with yesterday? Yesterday, we finished up by evaluating trigonometry on the quadrantal angles, which are the x and y axis. Okay? In order to be successful with evaluating on quadrantal angles, there's a couple things that you need to be good with. First and foremost, you need to know your radians to degrees and degrees to radians backwards and forwards. You need to know simply where you are going to land. Then you need to know which trig functions use which letters x, y, and r, and in what order, obviously. The only other thing that you have to think about is when you are on one of these axes at a quadrantal angle, it actually doesn't matter what value you choose for x or what value you choose for y. That's not important. All that is important is that you know where they're positive, where they're negative, and you remember that the radius is always a positive number. So whatever value you choose for, let's just say here, y to be, you could have said y was -5. It would not have mattered. The radius would have been 5. And either way, the answer still would have been undefined because secant is over x. But that's what's up with that. Okay? Okay. These kinds of questions could be thought of as being like, tiny math riddles, if you will. Tiny math riddles. And the way we do that is we decide where this is true and where this is true. Once we've decided where these two things are true, we look for what they have in common, and that's where we draw our triangle. Our job is to find cosine and tangent of theta using this information. We know that sine of theta is 3/7. Now, this is obviously not one of our special angles, and that doesn't matter. That's not important. What we need to know, though, is what letters does sine use? Sine uses y over r. So what I've been told here is that my y value is +3. Which two quadrants, out of 1, 2, 3, 4, which two quadrants will y be positive in? So we've got our two quadrants. Which two quadrants has y being positive? 1 and 2. So the first statement is true in quadrant 1 or 2. The second statement says tangent theta is less than 0, and less than 0 means negative. Tangent's letters are y over x. How is it possible that a fraction is negative? How does that happen? What makes a fraction negative? A negative in the numerator. Is that the only way? Negative in the denominator. What about both? Can it be negative in both? No. So one of these two things has to be negative. So in which two quadrants can we find one of the two negative but not both? Quadrant 2 has y negative. 4 has x I said this backwards. Quadrant 2 has x negative. Quadrant 4 has y negative. So this is going to occur, tangent is negative in quadrants 2 or 4. Well, the one quadrant where both things are true is quadrant 2. So that is where I'm going to draw my triangle, in quadrant 2. We know y and we know r. Y is 3, r is 7. I don't know x, but what do I know about x, where I am? Yep, it's negative. I need to solve for x because I'm going to need x to find cosine, and I'm also going to need x to find tangent. How do I find a missing side of this right triangle, though? Pythagorean theorem. Yep, that'll do it. Got to do the Pythagorean theorem. X squared plus 3 squared equals 7 squared. Subtract 9 from both sides, and we get that x squared is 40, and we're going to take the square root of both sides. We're not going to say plus or minus. We're in quadrant 2. X is automatically negative. But we can't leave it as the square root of 40. I mean, we know it's negative, but we can reduce the square root of 40. The only perfect square that goes into 40 is 4. It goes in 10 times. Square root of the 4 comes out. The 10 is hung up. We've reduced radicals more than once in this class, so we don't need to relearn it. You already are good at it, I hope. There. We've got x, we've got y, we've got r. We can easily find cosine and tangent at our theta. Cosine of theta is, well, cosine uses x over r. So that is negative 2 root 10 over 7. Tangent, y over x, which we've already mentioned up here. The y value is positive, but the x is negative. That means the fraction's negative. 3 over 2 root 10. Now, technically, you should rationalize your denominator, multiply the top and bottom by root 10. If you do that, you'll get negative 3 root 10 over 20. It's the same answer, though. I don't see a reason to rationalize the denominator unless I have to. Anybody want to ask me any questions about this one? Anything at all? It's the first time you've seen one like this. We've had to think about what quadrants to draw things in. Okay. All right. Then we'll say everybody's good. Let's do another one. It says secant of theta is equal to 3. Wow, okay, we have a small problem here. Trig of angle, trig of theta, is always a ratio of 2 side lengths. So what's the other side length that's not written? You can say it louder, Seeger. 1. It's 3 over 1. No. Trig of theta, sine, cosine, tangent, secant, cotangent, doesn't matter, is always going to result in an angle. A fraction of side lengths. We just need to know which 2 side lengths we have. Secant is the reciprocal of cosine. Cosine is x over r. That makes this r over x. We know r, we know x. X is positive. In which 2 quadrants can I find x being positive? 1 and 4. They're both on the right side. Oh, by the way, free money. We already know one of our 2 answers. Cosine of theta. We don't have to do any work. What is cosine of theta? 1 over 3. Because it's the reciprocal of secant of theta. We already know one of the 2 answers. No work required. One of the answers is 1/3. That one, though, we have to work a little bit for. This one says sine of theta is positive. Well, sine is y over r. That guarantees that y... This looks horrible. There. This guarantees to us that y is positive. Which 2 quadrants has y being positive? 1 and 2. The one that they have in common then? Quadrant 1. So we're going to draw this triangle in quadrant 1, where everything is positive, x and y. We know r is 3. We know x is 1. I had to solve for y. We know it will be positive this time because we're in quadrant 1. We solve for it the exact same way we did last time. Quadratic formula. Pythagorean theorem. One squared plus y squared equals 3 squared. So y squared is 8. We're going to take the square root of both sides. I'm going to come over here and do it. But we have to reduce the square root of 8. Just like 40, the only perfect square that will go into 8 is 4. This is 4 times 2. The square root of the 4 gets to come out. The 2 is, and then you have a 2 stuck inside. So what we get is 2 root 2. This is the square root of the 4 that came out. 2 root 2. Ready to finish it up. Cosine theta. That's the reciprocal of secant. So it's just 1/3. Because we were given 3/1. But in case you don't remember that it's the reciprocal, you could say, oh, cosine is x over r. Either way, you're going to get that 1/3. And the last one for these is tangent. Tangent is y over x. 2 root 2 over 1. There it is. Questions, comments, concerns, what ifs, why didn't we's, could we have's, anything like that on these little math puzzles where you have to figure out which quadrant you're going into. No? You sure? Okay. Well, I mean, hey, maybe that means that we're all really good at trigonometry already. Fingers crossed. Show of hands. How many of you have ever operated a ceiling fan? Like 2 people raising their hands? Like, show of hands. How many of you have operated a ceiling fan? Okay, like everybody in the room, right? Everybody in this room has pulled a chain on a ceiling fan before, right? We've done this. Great. And you're aware that pulling the chain on the ceiling fan changes the speed, correct? Great. You don't need to draw this. You just need to pay attention for a moment. Those speeds are off, low, medium, and like some of my students, high. I didn't call you out, Daniel, but do you have a guilty conscience? He just says, I'm not high. He says, you the fuzz, you wired? Actually, I am. I'm literally recording right now. 0, 1, 2, 3. So let's say that these speeds are 0 through 3, okay? These are chain pulls. All right. So let's say you go home and you notice that your fan is on. Is your fan on typically? Okay, let's say you go home and you find that your fan is on medium right now, all right? Your fan is on medium, which means you haven't had to pull the chain at all yet. You walked in the door, fan was on medium. We cool here? Awesome. You know that if you pull that fan chain one time, your speed goes up to high, correct? What happens if you pull it again? Goes to off, all right. And then if you pull it one more time, you're low. And if you pull it a 4th time, it's back to medium. What this means is pulling this chain 4 times is essentially the same as doing nothing. Can we agree to that? I mean, if it was off and I pull it 4 times, let's see, 1, 2, 3, 4. If it was off and I pull it 4 times, it's off again. So it seems like this fan speed pattern repeats itself every 4 pulls, doesn't it? And this could be a beneficial pattern to you. Let's say you are stricken with some OCD. Some people are. One of my good friends from college was. And she had trouble leaving the house. She had to take pictures of stoves, windows to make sure they were locked, doors to make sure they were locked, pictures of cats to make sure they hadn't escaped, and things like that. And then she would get in the car and go through the pictures, reassure herself that everything was locked, the cats didn't escape, yada, yada, yada. So let's say you are unfortunately stricken with OCD and you have this thing where you can only pull this chain in multiples of 5. Okay, this is a thing. This happens to some people. It can only happen in multiples of 5. And you come home, your fan is on medium, and doggone it, you need it on low. Is there a way to get to low by pulling it in multiples of 5? Well, of course there is. There's not a way to get to low and pulling it in multiples of 4 because the pattern repeats itself every 4. But if you're pulling it in any other number other than 0s and 4s, you'll get there eventually, right? So let's see. So you pull it once. 1, 2, 3, 4, 5. Crud. I need it on low. 1, 2, 3, 4, 5. Crud. I need it on low. 1, 2, 3, 4, 5. Whew. There it is. It took 15 chain pulls, but the point is it was doable, right? Looks to me like I have a pattern that is predictable and can be used in the future of our OCD chain pulls. Again, not making light of the situation, where we could just come home and go, all right, I now know that if I need to go down by 1, I have to pull it 15 times. Because you can only go in multiples of 5. Because you know if you do one more multiple of 5, now you're at 20 pulls. 20 pulls is a multiple of 4, which means you did nothing. Make sense? Repeatable pattern that can be predicted, and the pattern has a set length of time that it takes. Length of time, yes? You know what else is like that in our everyday lives? Tides, moon phases, seasons, I don't know, hand movement as it goes around the clock. All of these things are called periodic events. Periodic events are events that repeat themselves on a known pattern. Now in mathematics, a function is periodic if there is some positive number c such that this is true. Now wait a minute, let's talk about what this is telling us. This is me adding a number to my inputs. This is me adding or subtracting on the inside. What kind of transformation is that? Shifting. That's all. Shifting, is it horizontal or vertical? Horizontal. A function is periodic if there is a way to shift it horizontally and it looked like you did nothing. If you took this setup and shift it 4 to the right, it'll look like you did nothing. This is periodic. And that shift, this one was a length of 4. It took me a length of 4 shift. That shift is the period of that function. So the period of my fan pull scenario was 4 chain pulls. The period of the moon phases, technically 28.5 days. The period of our tides, roughly 12.5 hours. The period of our seasons, 1 year. It's how long it takes horizontal shift to get the exact same thing. Sine and cosine have a period of 2 pi. And that should make perfect sense. Because here, I'm sitting right here looking at Tn, right? And what does 2 pi represent for us? Full circle. And if I go, whee, and I spin myself all the way around a full circle, I'm looking at Tn again. Sine and cosine repeat themselves every full circle. That is their period length. Every 2 pi radians, or 360 degrees, sine and cosine say you've done absolutely nothing. You stayed where you were. No, you didn't. You moved. We get it. But the trig doesn't know that. Now, tangent repeats itself every half of a circle. So sine and cosine, and their reciprocals, repeat themselves every full circle. Tangent, and its reciprocal, repeat itself every half circle. Isn't that neat? This gives us the ability to evaluate ridiculous trigonometry by hand. I have no idea how many degrees 1,201 pi divided by 2 is. Someone in first period said it was like 180,000 something degrees. It's a lot. I have no clue where that is. But what I do know is that 1,201 is an odd number. And if I divide that by 2, what's my remainder? 1. That means I can write sine of this ridiculous fraction slightly differently. So now I have 1,200 pi over 2 plus 1 pi over 2. That gives me the 1,201 pi's over 2, right? I split it apart. I just broke the fraction apart. Simple before pre-algebra mathematics. And, you know, 1,200 divided by 2 is 600. Well, what is 600 pi in terms of circles? 300 full circles. Because it's a multiple of 2 pi. If you divide this by 2 pi, so then other than being really dizzy, would turning 300 circles change where I was looking if at the beginning I was looking at Tn? I'm looking at Tn, I start spinning. 300 circles later, I'm looking at Tn again. That means these 300 circles effectively do nothing. It might as well have said 0. Just like pulling your fan chain 4 times was the same as doing nothing. You might as well have not pulled it at all. And we can evaluate sine of pi over 2. You mean these twos? Well, I was just looking at 600 pi and I noticed that it's a multiple of 2 pi, specifically 300 times. And we can evaluate sine of pi over 2. That is one of our quadrantal angles. Scoot-oop. Pi over 2 is halfway between 0 and pi. It is here. That's the positive y-axis. On the y-axis, there's no x. We could pick a value for y. Pick one. It doesn't matter. 1 sounds good. What's the radius of that circle then? 1. All right. Let's evaluate. Sine uses y over r. So sine of pi over 2 is 1 over 1. Ta-da! So this equals 1. No calculator. All because of periodicity. That's the adjective to describe something that is periodic. Or is it? Wait, periodic is an adjective. So what is periodicity? English is hard. Okay. Would you like to ask me any questions about how to use the period of sine to evaluate that expression? All right, nobody's got any questions about that? Then we'll move on to this one. Let me tell you what this is not. This is not 8 pi. You are not allowed, it's not cosine of 8 pi. You are not allowed to subtract these arguments. You're just not allowed to. And it should make perfect sense to you why you're not allowed to. I mean, have you ever just been allowed to subtract arguments? Does this equal the square root of 8? No. You can't just subtract arguments. That's not allowed. Math doesn't change just because it looks different. So if you can't do it here, you can't do it here. But what you can do is notice that this argument is exactly 8 pi more than this argument. And do you know what these 8 pi are? What is 8 pi? What's that? 4 circles. Nowhere near as dizzy as 300 circles, but still just as useless. Turning 4 circles does not change where you are. So they can be disregarded. That means this is equivalent to cosine of 20.45 pi minus cosine of 20.45 pi. Do I know what cosine of 20.45 pi is? No. But I do know that anything minus itself is always equal to the same value. 0. So it's all about ignoring extra period lengths. They don't do anything for you. Turn in full circles. Other than looking goofy, hasn't done anything for you. What do you think about it? Nothing happens to them. It's equivalent to no circles. If I was looking at you, and then I spun around exactly 4 times, where would I be looking? Be looking right at you again. Might be looking at multiple versions of you because I might be cross-eyed at that point. But the point is, I'm facing you again, which means I've effectively not changed where I was looking, so I could have just not done it. And they could just be ignored. They do nothing. And this last one. Tangent repeats itself every half a circle. So this is 9 half circles. And tangent can ignore half circles. They don't do anything to tangent. So this is the same as saying tangent of pi over 4. And ignoring the half circles. They did nothing. Because that's the period length of pi. Or that's the period length of tangent, pi. Repeats itself every pi. Now we just evaluate tangent of pi over 4. Pi over 4 is which quadrant? First quadrant, because it's halfway between 0 and pi over 2. It's quadrant 1. And what is 180 over 4? 45. So this is a 45-degree reference angle. That makes that a 45, 45, 90, which has side length ratios of 1, 1, root 2. Tangent uses y over x. So tangent of pi over 4 is 1 over 1, which is 1. Boom. Again, I ask, would anybody like to ask me any questions at all about this material?
So it equals the same this way as it does this way?
Yes. So turning full circles in either direction does nothing to sine and cosine. Turning half circles in either direction for tangent does nothing. Yep. I mean, think about it. If I'm looking at you and I spin to my right a full circle, or if I spin to my left a full circle, I haven't done anything.
Yeah.
Now, tangents values repeat every half circle. It's no longer a coterminal angle. You see, for these, the full circle puts you at a coterminal angle. For tangent, you're right. A half a circle does not put me somewhere coterminal. But tangent, its values would repeat. So this is quadrant 1, right? If I were to turn half a circle from here, and it doesn't matter if I go this way or if I go this way, either way, I would be down here, correct? And if you look at it, do you remember vertical angles from geometry? That would also be a 45-degree angle. And here, both values would have been a negative 1. And if we had done y over x, we would have gone negative 1 over negative 1, which gives us back positive 1. So yeah, the 9 half circles does not land me here. It doesn't. It actually lands me here. Because an even number of whole circles puts me back here. But its values, because the x and y are both negative, the negative signs cancel, and it repeats its output value. Think of it as an x comma y. It repeats its output. Okay? Okay. We've talked a lot about the unit circle. I've said it a bunch of times. By the way, it's right here. Look at all that stuff. Holy guacamole. My grandmother says holy buckets. Assuming that means like the bucket has a hole in it and it leaks. Anyway, talked a lot about the unit circle. What is the unit circle? It is a circle that is centered at the origin at 0, 0. And it's called a unit circle because specifically its radius is 1, which you can see. That's why every time I've done one of these quadrantals, I've chosen the value of 1. You didn't know it, but I was forcing you into the unit circle. Anyway, the unit circle does some neat stuff. Remember, sine of theta is supposed to be y over r, correct? But if r is 1, because you're in the unit circle, sine of theta is just equal to y. Cosine of theta is supposed to be x over r. But if r is 1, cosine of theta just gives me x. That allows me to write any coordinate that's on the edge of the unit circle. Instead of writing it as x comma y, the x and y can be replaced and be written as cosine theta comma sine theta. Because in the unit circle, x is sine theta and x is cosine theta and y is sine theta. So any coordinate on the unit circles x, y instead can be written as cosine theta comma sine theta. You know what? Please go back to this box where we were not in the unit circle. We were in a generic xy plane. Here, r is any number. How do you get y by itself? Multiply by r. If you multiply both sides by r, what you're going to get is y equals r sine theta. See? Put that r right there. Y equals r sine theta. If we were in the unit circle and r was 1, we would get y equals sine theta, which is what we just said. And the same thing here. Multiply both sides by r, and you'll get x equals r cosine theta, meaning r times cosine theta. And if you were in the unit circle, r would be 1, and you get x equals cosine theta like we just said. Do you know what this allows us to do? It allows us to write any x comma y point using trigonometry, using r and theta. Instead of x comma y, it can be written as r cosine theta comma r sine theta. Almost like there's a whole nother coordinate system that instead of using x's and y's, it uses r's and thetas. And there is. It's called the polar coordinate system. And you will learn a lot about it in AP Pre-Calc next year. We call XY the rectangular coordinate system because, you know, a coordinate pair can make a box like that. These actually make circles. It's a circular coordinate system instead of rectangular, which should make sense to you because sine and cosine and circles and all that crap, right? Don't worry, we're not going to do that in this course. I'm just getting us up to that ability so that way at the next level you are prepared to handle that. Anyway, go back to the box we were just in. So yeah, on the unit circle, r is 1, so r cosine theta is just cosine theta, r sine theta is just sine theta. That's great. And of course, the reciprocal functions are still there, and they still do exactly the same thing they did before. Wait a minute. This says y is sine theta. X is cosine theta. Tangent to theta is y over x. That's not new. But there must be a nerd out there somewhere, and I'm not done. There's definitely a nerd out there somewhere. Someone that is paying attention and is thinking about things and might have just realized something profound. If y is sine theta and x is cosine theta and tangent of theta is y over x, Donald? Are you volunteering something profound? Yeah. Tangent of theta must be equal to sine theta divided by cosine theta, because that's what x and y equal. Wow. This is called a trig identity, one of many. Many. But that would be the first one you have learned because it's obviously true in the unit circle. And actually, it's true in any circle. It doesn't matter because the r's cancel out on the top and bottom of the fraction. Like r sine theta over r cosine theta, the r's cancel. Isn't that neat? So stinking neat. Anyway, y is the unit circle in the notes if I don't have it memorized and I don't want you to have it memorized. Because I wanted you to notice something about it. In quadrant 1, you have x and y positive. In quadrant 2, unfortunately, only y is positive, but x is negative. Oh, well, I didn't mean to do y and then x. It doesn't matter. In quadrant 3, x and y are both negative. In quadrant 4, x is positive, but y is negative. I'm going to put some letters on this thing. Here they are. A, S, T, C. All students take calculus. Of sine, cosine, and tangent, all are positive here. Sine is positive here. Tangent is positive here. Cosine is positive here. All are positive here because x and y are both positive. Sine is positive here because it's y over r. Tangent is positive here because it's y over x and the two negative signs would cancel out. Cosine is positive here because it's x over r. All students take calculus. This just tells us when our basic 3 trig functions are positive. That helps us do these kinds of questions that we started the lesson with. ASTC. An acronym? Yeah. Acronym. ASTC. But I think an acronym is... No, I guess it counts. It doesn't have to be a word. Yep, ASTC. So flip it. (15 pi over 4). It would be great if you knew where that was. How many times does 4 go into 15? 3 times. What's the remainder? So 15 over 4 is 3 3/4. So we are going to go to 3 pi and then 3/4 of a pi. So if I go to 3 pi and then I go another 3/4 of a pi on my way to 4 pi, what quadrant do I land in? Quadrant 4. And it's an over 4. So what is the size of the reference angle? 45 degrees. You see, I don't need to know what this is in degrees. Who cares? I know it's almost equal to 4 pi. See? 1, 2, 3. This would have been 4 pi. So 1 pi, 2 pi, 3 pi, and 3/4 the way to 4 pi. That makes that a 1, 1, root 2 triangle. Oh, but y is negative. And sine is y over r. Talk to me if you have a question. By the way, 4 pi is 16 over 4. So you could have thought of it as a pi over 4 before 16 over 4. We got time for this one more. And we'll call the notes there. It doesn't matter. They're all the same kind of examples, just using periodicity. Which one spooks you more? 660 degrees or 8 pi over 3? What quadrant is this in? You don't know? See how crummy degrees are? Notice that it's 300 degrees more than 360. Quadrant 4.
Oh wait, isn't the left side 2 pi?
0, 1 pi, 2 pi. So 0, 1, 2, 3, 4, 5, 6. This is even pies. This is odd pies. This is quadrant 4. How many times does 3 go into 8? 2. What's the remainder? So I'm going to go to 2 and 2/3 of a pi. Here is 0 pi, but it's also 2 pi. So if I go another 2/3 of a pi, where do I land? Quadrant 2. It's an over 3. So what size is the reference angle in degrees? 60, because 180 over 3 is 60. So you fill out your 60-degree angle, and then you do tangent there.
How is that quadrant 2?
How is this quadrant 2? Because it went 2/3 to the next pi. We'll have to call it there because the bell's going to ring in less than a moment. Thank you, nerds.